Hello, welcome to session number 29 in the series Analog Circuit Design using ADS. My name is Anurag Nigam, and continuing in the series, I'm going to cover the design of a third order Sigma Delta Modulator, which is an all digital design, MASH 111 architecture. And as you can see in the diagram here, there are three accumulators which are for three different orders, right? So this is a first order accumulator, that's the second order, and it's the third order. So first and second order noises is compensated, the third order is not compensated. Now here I'm going to first design a 1-bit accumulator, and then I will do a 12-bit accumulator here, and I can do a 16-bit accumulator if I want, but because this circuit operates at a low frequency, but then uh, you have to run through that many 2 raised to n cycles for this PLL to stabilize, right? So that's why I'm not doing 16, I'm going to do a 12-bit Sigma Delta Modulator, right? So these accumulators are going to be 12 bits. So let's do a 1-bit accumulator, and then from there we go on to do a 12-bit. Now here I also wanted to share with you that I'm going to use a lower divide ratio. So I'm going to choose a crystal. Usually in Wi-Fi you use a 40 megahertz crystal. I'm going to use a 80 megahertz crystal, and my frequency tuning range is 3.6 gigahertz to 4.7, which would translate to 3 by 2 of that, because there is a output mixer stage. So that will cover your 5.85 to 7.15 Wi-Fi 6E, right? So for that I'm doing this design, right? So I'm going to use the CTS, for example. This is an example of a CTS model 148 OCXO, right? And here there is a phase noise information here for this particular oscillator, right? So this phase noise information at 100 megahertz, it's over here, right? So what you expect is that that the divide ratio would add up to this phase noise, right? So you can go, so let's say the divide ratio is 45 to 60 in this case, right? So 60 is the worst case, so that would basically bring down this phase noise by minus 35 dB, right? So if you are operating at 1 kilohertz, for example, then this is minus 140, so you can expect minus 105, and at 10 kilohertz you can expect something like minus 115, right? So something like minus 115, minus 120. So again, you can notice that these OCXOs also deteriorate with higher the frequency. So I'm going to use a 80 megahertz crystal here, right? So with this put aside, let's go ahead and design this Sigma Delta Modulator. So I'm going to design the sub blocks first. So first thing which I need to design is a master slave flip-flop, so, or MSD FF, right? So I'm going to name that as MSD FF. MSD FF. And the design is very simple. I'm going to use a transmission cell, and I want to provide a reset also. So I'm going to use a transmission cell, and then I need a through path. So I'm going to use a NOT gate. All right. And I'm going to use two such NOT gates because I need a buffer. So I'm going to just repeat it. Okay. And then I need a feedback path, which is going to be the same TX cell, but then connected in a feedback fashion, right? So that will be connected in a feedback fashion. Okay, so the connection for the master is very simple. Okay, and then I'm going to have a pin which I'm going to call VDD, and then I have got ground, right? And I have a D input, so that's a D input, right? And then I'm just going to add VDD and ground. VDD, that's a VDD, that's a VDD, that's a VDD, and that's a VDD. And then I have got ground, that's a ground, so that's a ground, that's a ground, correct? And then I have got clock, right? So I'm going to call this as clock, and I'm going to generate a clock and a clock bar, right? So I'm going to use this inverter because this is a low frequency. I can use this inverter, right? So very simply put, this would be the clock node, this will be clock bar, right? So let me name this node as clock and this node as clock bar, right? So now this is clock bar while this is clock bar, and this is going to be clock, and this is going to be clock. So they are operating in tandem, right? So they are operating in tandem here. So I think this is clear. Now what I'm going to do is I'm going to put here the same block again. So I'm going to repeat that block. So I'm going to copy this block, which I have to repeat, right? So I'm going to copy that over here, and then I am going to introduce a reset, right? Okay, so the simplest reset I can introduce is going to be in this path over here itself. So all I need is I'm going to extend this way, and here they have to reverse, right? So basically, okay, so I will introduce another transmission cell over here, right? And this is not controlled by clock, this is controlled by reset, right? And all I need to do is I should be able to pull this node up, right? So I'm going to use a device which is going to be a PMOS device, right? So I can go inside and just copy that PMOS device. So I need this PMOS device to pull that node up. So I'm going to say edit copy, and then I'm going to say edit paste over here, and I want to pull up this node with the reset, right? So when this goes low, right, when this goes low, then this path is disrupted, right? So let me see if it makes more sense to put this feedback path on this side, because I need to disrupt both the paths, right? Okay, let's see that if it'll work. Okay, so this will disrupt both the paths. So this one I'll connect over here, and this will be my Q output. So I will have a Q output over here, So that's my Q output, correct? And then I am going to have this controlled by reset, right? So I am going to have a reset pin, which is over here. And then I am going to have, so this is going to be pulled up. So if this is pulled up, right, so that will give a state. Okay, so here this node is also VDD. Okay, and this node are the same, so this is wrong. So this node and this node are the same, so this is going to be reset, and then there's going to be reset bar. So I'm going to put in another, this guy, inverter over here. Correct? And then I am going to have RST and RSTB. So I will name this node as RST, and this is RSTB. Correct? So when reset moves low, so let me see. So when reset moves low, reset bar moves high, so this path is disrupted. So I'll name this node as reset. Okay, so I have one inversion over here and one inversion over here, but for this state I have a reset here. Okay, so let me try to understand if this is gonna work. And I am going to pull this up, so that means that this will be pulled down, so this will be a clear, right? This will be a clear, not reset, but it's okay. Fine. So let me just make sure if my logic is correct, right? Okay, I have a little bit of confusion here, whether this reset is going to work. So let's just make a symbol for this and test it out, right, and see if this works. Anything missing here? No. So let's make a symbol for this master slave D flip-flop, right? Okay. And I want to make a small symbol, right? Reset and ground I want to keep below, right? And clock on the left, VDD up. So clock on the left, and reset below, and ground below. Correct. And then this VDD up. And to remind me that this is a negative edge triggered, I'm going to put a bubble on the clock. Hang on a second. Okay. So here, that said, this is over here, and I'll put a bubble here. Okay. So here I have got a master slave D flip-flop with the clear. Actually, this is not a reset, a clear. Let's see if this works. Right, if it doesn't work, then we don't need this reset. But okay, so let's test this. So I'm going to make a new schematic, and I will say test msdff, create a schematic, and I am going to put in a symbol for this. Right. Okay, and I'm going to operate this from 1.5 volts. Sorry. So I'm going to operate this from 1.5 volts. So I can copy all that stuff from test NOT gate also. So that's okay. Do I have a test NOT gate? No, I don't. So test 2x3, that's also okay. So test 2x3 cell. Okay, so I'm going to copy the supply. This, probably one of this, and one of the capacitors, and a transient simulation. Control C. I cannot close before I paste. That's the problem with the. Okay. Control C. Then Control V. Control V. So there you have it. So I am going to have this as Q, and I am going to have this as D. This is the supply. So Q is supposed to follow D. And let's say I operate it at 1 gigahertz, though in this case it is not going to operate at 1.5 volts and 1 gigahertz. So that's going to be a duty cycle of 0.5, so 0.49 and 0.1. 0.1. Okay, so that's going to be the clock, right? And I'm going to put in here another pulse for D. Okay. Okay, I think there's something called edge here. Is there? No. This is VT pulse. It's a time domain pulse. This is a frequency domain pulse. That's okay. So here, peak voltage is 1.5, sorry. Okay, so I'm going to have a D over here, and I am going to introduce a D with a frequency of uh, okay, so with twice almost, right? So let me put here twice the time period, so basically zero point 0.5 here, and let's put here 99, right? And clock comes later, so let's introduce 0.25 as the delay, or rather I will introduce here uh, another pulse, right? So I will put here a delay of, let's say, 2, right? Okay, and then I need to put here a ground, and for reset also I'm going to put in a pulse here, and I want to put in a frequency of 1 megahertz, or let's say whatever is the crystal frequency, right? So let's say 80 megahertz, 80 megahertz, sorry, right? And the width of the pulse I'm going to put here very small, and here I'm going to dip it, so I'm going to put here 1.5. Okay, so I have to reverse this, right? So how do I reverse this? Okay, so I'm going to reverse this. So I'm going to introduce a pulse width of, let's say, 0.5 nanoseconds, so that's fine. And I'm going to give a delay of, so before I hit the clock, right? So I want to put here 1 second before that. I'm going to introduce that pulse, right? And I need to invert this, right? So I'm going to just invert this using an inverter, doesn't matter. So let's put here a static gate, that's the static gate. Okay, so this is going to be VDD, and this is going to be ground. So whatever is applied is going to be reversed here like this. Okay, fine. So this being done, I'm going to simulate for 20 nanosecond, maybe steps of 0.1 nanosecond, and then I'm going to name them. So this is going to be reset, this is going to be clock, and this is going to be D, this is going to be Q, correct? And then I'm going to hit simulate. So if everything is okay, I should see a clear. The D will work properly. Okay, so first I want to see relationship between D and clock. Okay, so I'm going to respond on the falling edge, right? So this is D, right? So I'm going to respond on the falling edges, right? And the next thing I want to add here is a reset. So reset comes here, and then it again comes here. So That's okay. So I want to just check over here, and then I'm going to look at Q. Okay, so I introduced a reset. Then this should represent, so this is behaving on the rising edge. Let me check that. So let me put you to pause and make sure everything is fine. Okay, here this slave has to be in tandem, so this is what we forgot to do. So here this would represent to, this will respond to clock bar, and this will represent to clock. This will respond to clock. Clock bar would be here, right? So let's try this again. Make sure. So this is clock bar, and this is clock bar, clock bar. Okay, fine. So here let's simulate this again. Let's see what happens here. Okay, fine. So now it makes sense. So this establishes a clear here. So basically this started at 0 only. That's why you couldn't see it. Because there is no clock here, right? So over here what happened? So this came in when D was low, is it? When D was high. Okay, so when D was high, this came in. So the output should have been high, but then it was pulled down. Right, so this should move to the left if I move this entire thing to the left. Okay, so let's say this is 1 nanosecond. And let's see if that edge moves. This should move. Yes, it did move. Okay, so this is really working. This is a clear, not a reset, but I don't want you to be confused, so I'm going to go ahead and change here to clear instead of reset. Okay, so this is going to be a clear. So let's rename this pin as CLR. Okay, and the remaining things can remain as is. All I will do is go in the symbol and change this to clear. So this one would be called CLR, and this node will be called CLR. Okay, so this is clear, and this I will name as CLR. And this has to be CLR. Okay, so when this comes in, it establishes a clear. So right now this was high following D, and then as soon as the clear comes, this becomes clear. Okay, so this is an asynchronous clear for this D flip-flop. Okay, so I'm all set with MSD. Now what I'm going to do is I'm going to do a adder, a full adder. So because in an accumulator I'm going to have a master slave D flip-flop giving a clock delay of 1 clock, and then it is going to add to itself. So that would be the adder, right? So I am going to implement a full adder. So I need a full adder. I can implement using static gates because this is not going to go up in frequency. So I'm going to say new schematic, and that is I will call f add or a full adder create schematic. Okay, here I am going to have NAND gates, right, and XOR gates. So I have a XOR gate, do I? So if I look under transmission gates, I don't have a XOR gate. So first of all, I'm going to implement a NAND gate here. New schematic. So I'll call this as NAND G. Okay, and in this case, I am going to just copy the transistors from NOT gate. Edit copy, edit paste. Okay, so here I have to just modify this to look like an AND gate. So I need one of this to be repeated here like this, and I need one of this to be repeated below like this. Correct. And sorry about that. Okay, and this one goes to here, and this one goes to here, and this is going to be VDD, this is going to be ground. So I have VDD, so that hooks up here. Then I have one input as this one, so this is going to be A, and then I'm going to have B. Okay, so this one is B, or rather I can put this one as B, doesn't matter. Okay, so I have got A and B, and then I'm going to have a ground. Okay, and that would be over here. So that's done, and that's a Q. Okay, so that's my NAND gate. So I'm going to make a symbol for a NAND gate. And as I want to keep it small, so this is not there. So this is in kind of in the center. And okay, and then I have a I will have a small bubble here. Okay. So that bubble basically going to remind me that this is going to be a NAND gate. Okay, so that's an AND gate. Okay, Then I'm going to modify this NAND gate to a NAND 3 gate. Okay, so all I have to do is I introduce a C terminal. So I need to copy this one over here. And I have to repeat this guy again. Right, and then this would be the C terminal. Correct? So okay, so let's introduce another pin and call it C. This is pin number 6. Okay, so that would be this one. Okay, so that's the 3 input NAND gate. So this is pin 6. So I will go back to the symbol and introduce another pin here, which will be pin C. So this one is C. This one I'll name as C. Okay, and here, let me see if I can adjust 3 of these. Okay. Okay, so it makes sense. Okay, so this is terminal C. Save it. Okay, so it tallies with my design here. Okay, so now I have got that, and I need one XOR gate. Okay, so I'm going to make a new schematic. Call this as a XOR gate. Okay, and here I am going to use a mux to implement an XOR gate. Okay, so I have got 2 terminals. One is A and then I have another terminal which is B. Okay, and I am going to introduce 2 NOT gates here. Okay, one over here, one over here. So I'm introducing 2 NOT gates. Okay, and I will introduce 1 NOT gate on the output too. So I have to implement a NOR gate, sorry, XNOR gate, and then it will be inverted to give me a XOR gate. Correct, and then I have got VDD. So that's a VDD, and then I have got a ground. That's a ground. We'll name them VDD. So all the VDDs I'll do. Okay, and then I'll do all the ground. Okay. Okay, done. And then I have got A and A bar. So this is going to be A, and this is going to be A bar. This is going to be B, and this is going to be B bar. Okay, so when A is high, so A terminal I'll name as here. So this is terminal A. So when A is high, then B goes through. So this terminal is B. When A is low, then B bar goes through. Right? B bar goes through. So that means that I don't need this one. Okay, so when A is high, B goes through. When A is low, B bar goes through. So that's an XNOR function, and then that will invert this to make a XOR function. So I'm all set with this. All I'm going to do is check this gate and an AND gate. So I'm going to check these two gates before I proceed. Okay, so I want to test a XOR gate. New schematic. This is test a XOR gate. Okay, so I'm going to test a XOR gate here. Okay, so I haven't made a symbol for this one, so let's make a symbol for XOR gate. Okay, I want this to be small, so let's keep this aside. Insert an arc. Okay, so medium. So that's that. I'm going to copy that. I'm going to flip it. And then I am going to put another arc. Okay. And then I'm going to put my inputs. So that's a A. That's a B. Oh, it's too small. Okay. Okay. So that's too small. Okay. So let's do this again. So over here, going over here. Okay. That's one of them. And let's just copy this, put it here, and let's put here another arc. Okay, and I need to repeat this. Okay, so I need to separate them out. That's a B. That's a B bar. Okay, and then this is VDD. And this is ground. And this is Q. Okay, doesn't matter. And then I need to remind myself that this is a XOR gate. So that will remind me that this is a XOR gate. And little adjustment here. Okay, so we're done with the XOR gate. Now I'm going to text the XOR gate. It's really working. And here I'm just going to take the testing of 2 by 3 cell, right? So I'm just going to copy those common things. Edit, copy, edit, paste. So I am going to clock this at 1 gigahertz and 0.5 gigahertz. So I'm going to clock this at 1 gigahertz. So that 1 gigahertz is equivalent to 49. 49, sorry. Correct. And 0.5 gigahertz. It's going to be 99. Okay, so that's my A input and that's my B input, and then I have a capacitor load that's over here. I have VDD and then I have ground. Okay, let's see if I'm recording. Yes. Okay, so don't worry about the time because this is a slightly bigger block. So please bear with me on the timing. I'm trying to do the fastest I can. Okay, so I am operating at 1 gigahertz, so roughly 2 nanoseconds is good enough. Steps of 0.1 nanosecond. Right, and here I'm going to have A and B, A and B and Q. Okay, so I'm ready for the simulation. So I'm going to simulate this. So I'm going to look at A, I'm going to look at B. So this basically generates all the states. And then I'm going to look at output, which is going to be Q. So when the two inputs are unequal, then output is high. So that's a XOR gate function. So XOR gate is functioning fine. Okay. So so there's going to be delay, right? But then this is a low frequency block, so it doesn't matter. Okay, so what I'm going to do here is I'm going to test a NAND gate also. So I'm just going to copy this cell, test XOR, copy the cell, and test XOR. So copy this cell to test NAND. Okay, and this goes under static gates. So here is test NAND. I'm going to replace this gate by a NAND gate. Correct? Okay, so I'm all set. So I'm just going to test the NAND gate. So I have A B, and Q, and I'll split the screen. So the output is low when both inputs are high. Otherwise, the output is high. Correct? So this is working. There's a delay here. That's okay. So this full adder would have these delays when I cascade them, right? Because I'm going to make a 12-bit, right? So clocking, I'm going to introduce delays. Okay. So that's fine. So now I'm going to make a full adder. So this is full adder. So I need two XOR gates. Okay, one and a second one. Okay, I could have done, sorry, I could have done another form of a gate, but I don't think it is going to be any faster, right? So I need a B, and C in input. So I have got A, then I have got B, and then I have got C in. Okay, so this is your A, B, C in. And then I have got NAND gates to generate the carry. So I'm going to use 3 NAND gates, 1, 2, and 3. And then the 3 input NAND gate over here. And we are all set. Okay, so I am going to have A with B. And then I'm going to have A with carry. Then I'm going to have B with carry. Right? B with carry. So I have got A with B, A with carry, and then B with carry. This is carry, so this is wrong connection. I should have a B with carry. So that's a B with carry. And then this is a AND OR. Okay, so this is going to be sum. And that's going to be C out. And then I'm going to have 2 pins which are going to be VDD. And then I'm going to have ground. Okay, so now I'm going to just name this as VDD. And this is VDD, this is VDD, this is VDD, this is VDD, this is VDD. And then this one is ground. And this one is ground, this is ground, this is ground, this is ground, ground, and this is ground. So that's a full adder, correct? And full adder is going to have delays, right? Okay, so I have got 8 states which I have to generate here to test this full adder. So let's make a symbol for this full adder. A, B, C in, S and C out. Correct? And then we have got VDD and ground. So just bear with me. Okay, so to remind me, I'm going to put here a small text which says that this is a full adder. Correct, so we are done with the full adder. So I'm going to test the full adder and then make a 1-bit accumulator, right? So I am going to test a full adder. Test FA. So I'm testing a full adder here. Okay, so let's see if that works. Okay, so that still works. Okay, so I have got a VDD, and then I have got a ground. Then I have got sum, and I have got C out. So that's a sum, that's a C out. So this is sum, and this is C out. Correct? And this one is operating at, let's say I'm going to operate, okay, I'm going to operate this at 1 gigahertz. So this is going to be 49. And then I'm going to operate B at 0.5 gigahertz. So this is going to be 9. Right. And then I'm going to operate 0.25 gigahertz the C in. So and I need to generate 8 of this, so this would be like 1, 2, 4 nanoseconds. So I'll generate 8 states: A, B, C in. So I have got A, I have got B, and I have got C in. Okay, so this is ready for testing. Okay, so I'm going to put in here A, B, and C in and split it out. So this is working fine. I want to look at sum, and I want to look at C out. Okay, so what that is okay, okay, so all states are working. Only thing is that this delay, so when I cascade this, okay, accumulators to make this thing, I need to compensate for that delay, right? These delays are coming from XOR gates, right? So that will be simple, not a big issue. So let's make a 1-bit accumulator. Okay, so I'm going to make a 1-bit accumulator. So let's put this aside. Don't clutter the screen. Okay, so I'm going to make here a new folder, and I'll call this as Sigma Delta blocks. Okay, so these are Sigma Delta blocks, and here I'm going to make a new schematic, call this as ACC 1-bit. Okay, and here I need a full adder, and in the feedback path I need uh, a D flip-flop. Okay, so I need a full adder, which is over here. Correct, and then I need a D flip-flop, and that D flip-flop should be over here, MSDFF. Correct. Okay, so this is going to work in feedback, right? Okay, hang on a second. Okay, so I am going to have two pins. One is going to be VDD, other is going to be ground. Correct? And so this is VDD. So that's VDD. That's a VDD. This is a ground. So that's a ground. And that's a ground. Correct? And then I am going to have D in and D out. So D in and D out. So this I'm going to say is D in. Correct? And the sum is going to be D out. Correct? So sum is going to be D out. So sum is going to be a D out. Okay, and the D out is going to be fed back in to a D input. Correct. And this is going to go to B. Correct. And then this is going to be C out. This is going to be C in. Correct. So I'm going to have a C in. So let's see if I'm recording. Yes. So I'm going to have a C in, which is this terminal. Okay. Doesn't matter. So that's a C in. And then I'm going to have a C out. So we're here. And then I'm going to have clock and clear. So I'm going to have a clock, which is going to be this one. What? And then I'm going to have a clear. Okay, so this is my 1-bit accumulator. Now, okay, that's okay. And the D4 is the 4th pin. Okay, then we have got other pins too. That's okay. So now I'm going to make a symbol for this one. So where did I create the accumulator? Sigma Delta blocks. New symbol. Okay, and I am going to make a symbol such that it is convenient to connect in the top level. So all I want is VDD and C out at the top, C in on the and D out on the right. Okay, so let's make this very simple. So I need VDD and C out on the top. So I'm gonna just rotate this, mirror this out. So this is VDD and C out on the top. Then I want D out and C in on the left side, that's fine. And then I want clear and ground at the bottom. Clear and ground at the bottom. And D in clock on the left. Just bear with me a second. I want to make the symbols as small as possible. Okay. Now to remind me that the clock is a edge triggered, and that too falling edge. Let me just put a bubble here. Okay, so I'm going to put a bubble here. Okay. So that's a bubble. Okay, so that's the 1-bit accumulator. Okay, so I'll call this as 1ACC. Well, it doesn't matter. Anyways, the name would be there. Okay, so that's a 1-bit accumulator. And I want to make another 1-bit accumulator, but this time I don't want the D out. So I'm going to copy cell. So, and D. So no D out. This is for the third order accumulator. So on that I don't want a D out, right? Okay, so I will copy this to Sigma Delta blocks. Okay, so here I don't know if it will allow me to delete this guy because this will not be in continuation now. Okay, and if I go to symbol, D out doesn't exist. So this will be accumulator without D out. So now I'm going to check if the accumulator is working. Okay. Okay, so now that we have a 1-bit accumulator, we are going to design a 12-bit accumulator. So in Sigma Delta blocks, you make a new schematic and you call it ATTN accumulator, sorry, ACCN. Okay, 12-bit. Okay, so I'm going to make a 12-bit accumulator using 1-bit accumulator. So here, okay, so what we're going to do, Okay, so we're going to cascade these, right? So we are going to have VDD and ground. That common pins are there, VDD and then ground, right? So they are there. So I'm going to name this as VDD. This is VDD and this one is ground and this one is ground. Okay, so these two are common here. Let's put them apart. Okay, so now I would have, just 1 second. Okay, I will start with the two pins. One is the clock, other is the clear. Right, so I'm going to start with clock and clear. Okay, so in this case, clock, clear will go to the clear and clock will go to here, the clock. Correct? Okay, and then you are going to have D0, D1, D2, and similarly D out, right? And C in, there will be a C in. So there will be another pin which I'll call C in, and that would be here C in. Right, and then I'm going to repeat these blocks. So I'm going to repeat this block 3 times. Okay, so here, okay, I'll place the D in D outs later on. So let's just cascade the clear portion, right? So here, let me put here scope for 4 of this clock and clears. Okay, so here I have clock and clear, right? So here the C out will go to the C in. Okay, so this is C out and that's C in. Done. And then I'm going to repeat this block. Okay, so I'm going to repeat this block again and again. So this is 3-bit, and then this is 4th-bit. Okay, so these are the 4 bits. After this, I'm going to put two inverters here, right? So I'm going to take a NOT gate, and static, and yeah, I'm just going to place 2 NOT gates here. 1, 2, and then again it will repeat 1 and 2. So these are buffers, right? So here, this is for the distribution of the clock and the clear signal. So this is going to be VDD. So this is VDD, this is VDD, and this is VDD, and this is going to be ground, and this is ground, and this is ground, and this is ground. So we are done with this. Now the next thing is I'm going to repeat this block. Okay, so I'm going to repeat this block again. So I'm going to take this over here. So now I have an 8-bit. So I have 8-bit now, and again I have to connect this. Okay, so now I have 8-bit, so I need another 4 to make a 12-bit. Okay, so another 4 I will make up to here. Okay, and then again I have to make sure that C out goes as a C in. Okay, so now what we have here is a 12-bit accumulator, and then it will have DI0 and DO0. So DI0, so I'll name all the pins. Okay, I'll start with DI0. So that's DI0. Then I have DI1. Then I have DI2. And then I have DI3. And then I have DI4, DI5, DI6, DI7. And the reason I am doing this is I just don't want to show you the final result. You can follow along with me to design this Sigma Delta Modulator. DI9, DI10, and DI11. Right? So these are your input pins. Let's connect them quickly. Okay, so now that we have done this, there is going to be a final C out here, right? So there will be one final C out over here, which will give you an overflow bit, right? And finally, I'm going to put in D out bit, D out pins, right? So on the right hand side, I'm going to have D out pins, right? So let's go ahead and do that. So we have got DO0. Okay, so we'll start with DO0, DO1, DO2, DO3, DO4, DO5, DO6, DO7, and then we have got DO8, DO9, DO10, and then DO11. Okay, so I'm going to connect these. Okay. Okay, so now that we have a 12-bit this thing, I am going to make a symbol for this one, right? So I am going to make a symbol for 12-bit accumulator. Okay, and in this symbol I'm going to put, so let's see how it shows up. I have DI0 to DI11 up to here, and then I have DO0, right? So here what I'm going to do is, okay, I am going to put ground clock and clear below. So I'm going to put ground, okay, clock, and this is a negative edge triggered clock, and clear below, and also scene I'll separate out. Okay, so here let me create some more gap here. Okay, okay, and then I am going to have C in over here, and then D0 to D11 over here, and then this is VDD and CO at the top, CO and VDD at the top. Okay, CO and VDD at the top. So I'm going to move this in, then I'm going to move this to the left by one position. Okay, so now I'm going to put here VDD and C out. Okay, so this is my 12-bit accumulator. Okay, and here I'm going to put in here uh, to remind myself that this is edge triggered falling edge clock. I am going to put here a bubble. Okay, so that's a bubble. Okay, and I'm going to put here a text. So insert text says 12-bit accumulator, 12-bit. Okay, so this is a 12-bit accumulator. Okay, so I'm done with one accumulator. Then I am going to make a copy of this with no output, no D out. So I'm going to copy cell to underscore ND. So that's going to be the third one, right? ND. Okay, and here I'm going to modify this to not have any outputs, right? So here, just one second. Okay, so I'm going to go to schematic here and replace all of this by underscore ND. Correct? So what I'm going to do is these would be gone, right? Okay, so let me just create this one without the outputs, right? And then this is not there, so all these are not there. Okay, and then I'm going to delete these and going to place these. Correct? Okay. Okay, now as they are symmetric, I can do this in one stroke. Let's delete these. Okay, and copy these four. And paste it over here like this. Okay, so now these fours are replaced. Okay, and then I'm going to delete this and again place these four, right? So that will go here. Okay, so done. So now this one is without this DO. So in this case, in the schematic symbol, I'm just going to remove all these DO terms. Correct? Symbol store. Okay, so we are done with without the output. Okay, so now we have two sets of accumulators. Now I'm going to check one of the accumulators and clock it at a low frequency. Let's say 100 megahertz. Okay, so just hang on a second. Okay, so to check this, I'm going to do a test accumulator, right? And I'm going to give in some input and see if it is adding to itself every clock cycle, right? So to do that, I'm going to create a test accumulator 12-bit, test ACC 12-bit. Okay. Okay, so now I am going to place that accumulator over here to check this. And here I need to give some input, right? So I am going to have VDD. So I'm going to have VDD, so I can copy that from any test bench. Okay, so that's the VDD and that's the output. In one of the clocks I'm going to copy in these, say Control C, Control V. Okay, so let's place them somewhere. Okay, so we have a 1.5 volt supply over here as a VDD, and then we have a ground over here, and we have a clock and then a clear, right? So now once this is done, I'm going to do a transient simulation. Fine. Okay, so I am going to place in these. Okay, and I'm just going to repeat them. 1, 2, 3, 5, 9, 11, and then I'm going to also have one for the C out. Right, so these are my terminations: D0, D1, D2, D3, D4, D5, D6, D7, D8, D9. What happened? D0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Correct? And that's 11. Okay. 3, 3, 6, 3, 9, 10, 11, 12. What happened here? D0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, and then one more, which will be for the C out. Okay, so this is for the C out. Done. And then I'm going to create two supplies here. One is 0, other is 1. So this is 1 and this is going to be 0. Right, so I will call this one as 1 and this one as 0. Okay, now what I'm going to do is I'm going to give it an input of, let's say, 5. So that 5 will become 10, 10 will become 15, okay, and 15 will become 25, and so on, right? So I'm going to name them as 0, 1, 0, 1, 0, 1. Okay, so this remaining I'll give a 0 input, right? And okay, so what this means is when the number adds to itself and it goes through a 4096 cycle, right? So it goes through a so if it is a 10 bit is 1024, it is 11 bit is 2048, 12 bit means it's 4096 states it will go through. So in 4096 states this accumulator will overflow 5 times, because if you add number to itself, then whatever number you enter, that many times the overflow will occur, right? So in this case another input is clear and C in. So in this case I'm going to give C in as 0, correct? So I'm going to give in C in also as 0, right? And then I'm left with these. So let's just name these first, right? So this is D0, D1, D2, like that, right? So let's go with D0, D1, D2, D3, D4, D5, D6, D7, D8, D9, this is D10, then you have D11, and then you have got C out, CO, correct? So this is that, and I am going to put in a cycle which is going to be uh, so if this is going to be 100 megahertz, for example, then its time period is going to be uh, 10 nanoseconds, right? And then the width is going to be 5 nanoseconds, right? So I would do a 499. So that's a 5 nanosecond. So that's driven at 100 megahertz. Next is I am going to have a clear signal. So before I put in a clock, I will introduce a clear signal. So let's go to when we did a master slave D flip-flop, right? So that master slave D flip-flop is under here, and when we did the test for that, right? So what did we do? We introduced a clock with a certain delay, and in between that delay, we introduced here the reset, right? So only thing is that the reset is going to be even much larger now. So what I'm going to do is I'm going to copy this one. Okay, so this is being driven at 1 gigahertz, but I'm going to drive it at 100 megahertz, right? So that's what I'm doing. The next thing is this. Okay, so I'm going to just say copy, and I'm going to say paste. Okay, so let's see what's happening here. I'm going to put here, let's say, limiting case 1 kilohertz, for example. So every time when I'm loading it, okay, I'm introducing a pulse which is going to be this wide, okay, and then it's going to have this rise time and fall time, fine, and then the delay is 1 nanosecond. So this one has the clock really starts at, let's say, 2 point. So the width is 5 nanoseconds, right? So let's do a delay of 5 nanosecond here. So within that 5 nanosecond, I am going to introduce here at 1 nanosecond, I'm going to introduce here a pulse, and that pulse would load. Okay, so the pulse would load. So let's name this as VDD. Okay, VDD. So the pulse is going to load the, or rather clear the previous counts, right? So whatever previous count was going on, right? So I'm going to clear that. right? So I'm just going to see for the one cycle how it's behaving. So I'm going to clear that with this pulse at 1 second, and then at 5 nanosecond I'm going to start the clock, and that will do a 5, then 10, and then 15, and then 15 plus 10 is 25, 25 plus 15 is 40, and so on. So that's what this output is going to be, correct? And here actually 100 megahertz, right? So 4096. So let me just do a little calculation. Okay, so if I do 100 megahertz and if I divide this by 4096, okay, so because, right, because that is going to be the frequency at which this should come. So this is going to be 24.4 kilohertz, is it? So this big number is there, right? So at this point the load will come again, or not the load, the clear will come again, or I mean need not clear it even. So once I do this, it'll automatically keep in loop, right? So that's fine, that's fine. So it's just when you set this PLL in the starting sequence, you should put one pulse. It's a mono pulse, and once this is done on clearing, and then whatever is the input, you can keep adding. Now if you change this input, you have to introduce this pulse again. So that's when you program the PLL. Okay, so having done that, let's go here and simulate it for how many seconds. So 0.1 nanosecond multiplied by 4096, 409 nanoseconds. So I'm not going to do for that long. Let's just look for 10 nanoseconds or 20 nanoseconds, right? Let's see. No, I have to do at least 100 nanoseconds, right? Okay, let's do 100 nanoseconds. Okay, and if everything is fine, I will have a result. Otherwise, I'll do a debug. So let me hit simulate. Sorry, let me put simulate and then put you on to pause. And then let this finish. Okay, so first round of simulation is done, and what we have over here, I did a small modification. I just removed the buffers in the clear path. Other than that, everything is the same. And here is what I have. So I feed in 10, 1, 0, 1, right? And then that 10 is added to, so I feed in 5, so 5 is added to itself, so that makes 10. So this is 1 0 1 0, so that's 10. Next time 5 is again added to 10, so that will be 15. So this is 1 1 1 1, and then next time 5 is added to 15, so that's 20. So this is 1 0 1 0 0, so that means that is 16 plus 4 20. Then the next cycle I have 1 1 0 0 1. So basically this is 16 plus 8 is 16, plus 8 is 24, plus 1 25. So 20 25, and the next is going to be 30. So it's 16 plus 8 plus 4. Okay, so 16 plus 12 is 28 plus 2. 28 plus 2 is 30. So this 5 keeps on accumulating over a period of time. And if I go through 4096 cycles, okay, then this accumulator is going to overflow 5 times. So whatever you feed in, that many times the accumulator is going to overflow. So if I right now see CO is totally flat, so it's going to overflow 5 times because I have fed in 5 into the accumulator. So basically this is accumulator. So if I put 3 of these accumulators, and then I am going to take the overflow bits and add a compensation network. So already this recording has been 1 hour 45 minutes. So I'm going to extend this to part number 2, where I do the compensation network and combine these accumulators with the compensation network to result in a MASH 111 Sigma Delta modulator. So I'm going to stop here. Thanks a lot. Thank you.